set of questions, and we are going to discuss the possible responses, and also we are going to try to justify why we are saying those are the correct responses. We'll give some brief explanations to why we are giving a justification of those responses as to be the possible responses to the given set of questions. So, as usual, our paper, understand, if it's paper 1, it comprises of 3 questions, and the first 2 questions, the theory questions, are 60 marks each. Then the last question, which is map work, is a question out of 30. So to give us a total of 150 marks in 3 hours. Right. Our questions as they stand, is question number 1, which is climate and weather, which is 60 marks, and geomorphology, question number 2, which is 60 marks, and geographical skills and techniques, which is 30 marks. Right, we go on to our questions. Right, our first question on climate and weather, which is question number 1.1, is based on the map, the sketch map, which is provided. We'll just try to analyze the sketch map so that we have a better understanding of what is happening on the sketch map. Right, if we see this sketch map is showing the Southern African subcontinent, and we are having this low pressure cell over the interior, and we are having a high pressure on the extreme east, and also another high pressure on the western coast of the Southern African subcontinent. Right, so by identification, we can safely conclude that this low pressure over the interior is what we call a thermal low. A thermal low in the sense that the low pressure over the interior is caused by intense heating. When the ground surface is intensively heated by the incoming solar radiation, we tend to experience a low pressure developing over the interior. Right, and also on the extreme west, we have a high pressure. This is our South Atlantic high pressure. And on the east, we understand this is our South Indian high pressure cell. So, and we need to analyze this situation of our isobars. We are seeing that the isobar here, the central isobar, which is in the innermost of our high pressure cell, is having a regular shape. But if we check, the next isobar is having an elongated shape, like this one here. Is a question that is going to be posed on the elongation of this isobar here as it is approaching towards the interior. We can see the distance here between the 2 isobars is not equidistant. It's closer on this part, but as it is on the side of approaching the coastal area, is elongated as indicated by B. Right, that's the translation of the illustration. We need to now go to our questions and try to answer the given questions. Right, based on the map which is provided. Right, our first question, which is question number 1.11. The season shown in the sketch map is, what is the season shown on the sketch map? Our season given there is our summer season. The correct response is summer season. Why are we saying it's summer season? If we check over the interior, we have a low pressure cell. That low pressure cell is caused by intense heating, and that is typical of summer conditions. We can only have a low pressure cell dominating over the interior during the summer season, where we have high amounts of incoming solar radiation. Right, moving on to the next question, number 1.1.2, it says lines on the sketch map that join places of equal atmospheric pressure are known as. We are referring to these lines with indication 1020, 1016, 1016, 1012. These lines are what we call the isobars. They join places of equal atmospheric pressure, and our atmospheric pressure is presented in hectopascals, in HPAs. The isotherms, the isoheads, the contours, they have got specific places that they join. Isotherms, they are for temperature. They are used to join places with the same temperature. Then isoheads, they are for rainfall. They are also used to indicate places with similar amounts of rainfall on a map. And I think we know this is an indication of high basis of the same deposit level on the map. So those are the responses. Moving on to the question, the atmospheric pressure gradient is the parcels. HA, we are seeing that line A is a line which is going in this isobar. We are trying to figure out the value of isobar A. We can figure it by using the isobars which are next to it. If we say high pressure cell going towards the low pressure cell over the interior, and our last isobar which is indicated here from the high pressure cell, the outermost isobar, the shaded part in the circle, it represents cloud cover. And these two digits are for temperature. The higher one is for maximum temperature, or what you call the air temperature. And the smaller one is for minimum temperature, or the dew point temperature. Then the pointing of this arm here is for wind direction. And the feathers here at the end of our pointing are for the wind speed in knots. Wind speed. And when we're indicating our wind speed, we indicate it like this. If there is one full feather, it represents 10 knots. If it's half, it means it's half of 10, which means it will be 5 knots. So when there is a feather which is smaller, it means it's 5, but when it's full, it means it's 10. So we want to check on our maps and identify a map that has got wind speed of 5 knots and also with the direction of wind, which is southwesterly. Right, by determining wind direction, we can safely eliminate W. W, this is not southwest, is northeast. Coming here, it's southwest, and also here it's southwest and southwest. But we are worried about the wind speed. This is 1.5, meaning to say it's 10 plus 5, 15. This is 2.5, meaning to say it's 10 times 2 plus 5, which is 25. This is half, meaning to say, which is 6 octaves. So with this high cloud cover area, so one point is the effect of high cloud cover, and the next point is that of high relative humidity. So because of item 1 and item 4, they match at D. That qualifies to be our correct response. Right, we go on to the next question. The next question is based on a matching column question. Right, a dash refers to higher temperatures in the urban areas with decreasing temperatures towards the rural areas. Right, what you are saying here, we are saying when we have a situation of an urban area with higher temperatures compared to the surrounding rural areas or the countryside, that situation is a situation of what we call a heat island. Whenever we're talking of temperature difference between an urban area and the surrounding countryside, remember, we are relating to temperature, and the temperature gives us a heat island. Pollution dome will be looking at the concentration of pollutants over the urban area. Right, a factor contributing to higher temperatures in the urban area. Basically, urban areas have got dense buildings. They are the ones that contribute towards higher temperatures. Green belts, we are looking at the introduction of vegetation and vegetative cover. Right, welcome learners, the continuation of our discussion of our climate and weather question. We are on question number 1.2. So the first question, on 1.21, it says, a dash refers to higher temperatures in the urban areas with decreasing temperatures towards the rural areas. But the situation where we have higher temperatures in the urban area compared to the surrounding countryside or compared to the surrounding rural areas, that's a situation of what we call a heat island. We are relating to temperature here. Urban areas having higher temperatures compared to the surrounding farmland or surrounding countrysides. That is the effect of heat islands. When we're talking of a pollution dome, we are looking at the concentration of pollutants. Here, the pollution dome mainly is concerned with the concentration of pollutants over an urban area. Right, moving on to the next question, number 1.22. The question says, a factor contributing to higher temperatures in the urban areas. Between the two, dense buildings and green belts, which one is most likely to cause higher temperatures in the urban area? Our correct response is Y. Dense buildings, they are the ones that contribute towards higher temperatures in the urban areas. Because of the effect of artificial surfaces, they tend to absorb heat, and also some of the buildings will be having shine surfaces, which will cause multiple reflections, and those multiple reflections are going to contribute towards higher temperatures in the urban areas. Right, we move on to the next question, number 1.2. Number 1.2.3. Heat islands are more dominant during which time heat islands more dominant? We have our heat islands dominating during the daytime. During the day, that is when we have high insolation. And because of that insolation, we tend to have heat being absorbed by artificial surfaces and also some of the heat being reflected, causing the temperatures to be higher during the day. At night, we experience long wave radiation, which results in the loss of some of the heat which has been absorbed during the day into the atmosphere due to the process of terrestrial or long wave radiation. Right, moving on to the next question, it says, dash would be an effective strategy to reduce the heat islands, the effect of heat islands. What can we do to reduce the effect of heat islands? The correct response is Y, planting trees. Right, we understand that trees have got a cooling effect because they produce shade and also because of the effect of transpiration by the vegetation leaves. So as a result, we tend to have a cooling effect because of the introduction of vegetation or planting of trees. Tarring of roads is actually a factor which contributes towards higher temperatures in the urban area because remember, tarmac surfaces are artificial surfaces that tend to absorb the heat. Right, moving on to the next question, number 125. It says, multiple reflections of the sun's rays in urban areas are caused by multiple reflections. When we're talking of reflections here, we are worried about shine surfaces. So the correct response is glass surfaces. Glass being a shine material, it means it has a tendency of reflecting the heat. So it will reflect the heat. Concrete surfaces, they do absorb, they don't reflect. Right, moving on to the next question. Heat islands are more likely to favor the formation of, when we have heat islands, we are likely to have the formation of rainfall. I will need to explain on that one. How does rainfall form because of heat islands? We are saying in the urban area, we experience a situation of heat islands. Right, we are saying, let's assume this is our urban area. These are our buildings in the urban area. Right. And we are saying this is a surrounding countryside, it's a rural area, and this is a surrounding rural area. Right. What is going to happen is because of the heat island, we are seeing that in the urban area, the temperatures are high. We have high temperatures in the urban area. So because of the high temperatures in the urban areas, what is most likely to happen? Because of the heat island, we are saying the urban area is having higher temperatures compared to the surrounding rural areas or compared to the surrounding countryside. So because of that, we are saying there is high temperature. We need to analyze the relationship between temperature and pressure. We know well that when we have high temperature, when temperature is high, it implies that it gives us a low pressure developing. And when temperature is low, it gives us a high pressure cell, which is likely to develop in that area. So we are saying because this is a rural area, we tend to have high pressure here because the effect of heat island is dominant in the urban area. And also in the rural area, there's high pressure. It's cooler in those areas. And here, because of the heat island, there's low pressure. So we can see now that there's pressure gradient, there's a high pressure cell and a low pressure cell in the urban area, and also a high pressure from the other side of the rural surrounding farmlands. So because of this effect, we tend to have air blowing into the urban area from the surrounding rural areas. The air converges in the urban area. As it converges, it rises. As the air rises, remember it reaches the dew point, and ultimately there will be clouds forming over the urban area, what we call localized precipitation. It will be localized. We have precipitation being received in the urban area here. Because of the effect of the heat island, it tends to cause a convective effect in the urban area, and apparently resulting in the upliftment of warm and moist air coming from the rural areas and causing precipitation over the urban area. and that is most likely localized precipitation. It won't cover the rural areas. It will just cover above the urban area, and it will be received in the urban area. So that is how urban heat islands contribute towards the formation of rainfall. And the other favoring factor for the effective formation of rainfall over the urban area is because of the presence of hygroscopic nuclei of condensation. What is it that we call hygroscopic nuclei of condensation? We are saying for condensation to effectively take place, there is need for some nuclei, and those nuclei, they facilitate condensation to take place effectively. So in urban areas, there are high chances of availability of nuclei of condensation above the urban areas because of different activities that happen in urban areas. For example, dust particles, we can talk of smoke particles released from industries and also released from vehicles. They will be readily available in the atmosphere, and they facilitate condensation to take place, such that we have effective condensation and precipitation formation over the urban areas. Right. Going on to the next question. Our next question is saying, dash is an effect of heat islands on people. The likely response is heat stroke. Heat islands are likely to cause heat strokes amongst people in the urban area because of excessive high temperatures. People are likely to be affected by heat stroke. Right, we move on to the next question. The next question is referred to the weather map below, showing the cold front of the mid-latitude cyclone. Right, we are seeing that there is a cold front here, or cold front, which is moving in that direction according to the key which is indicated here. So we are seeing the coming of the cold front over the Western Cape region of South Africa, which is apparently affecting places in the western coast, and with high chances of rainfall at 80%. So we want to use that information to answer the questions. Right, the first question is saying, the general direction of movement of the cold front is. Right, you can check here on our indication of the wind direction on the key. We are seeing that they is going in that direction. So basically our cold front is moving eastwards. The movement direction of mid-latitude cyclones, over which the cold front is part of, is they move from the west going to the east. So it's an eastward movement direction. Why does the mid-latitude cyclone move in this direction? As answer to the previous question, why do they move eastwards? I will also want to make an illustration there of why they move eastwards. We want to make a justification of the reasons as to why mid-latitude cyclones move from west to east. Right, we'll go back to grade 11 content, where we did the planetary winds on a global scale. Like, we want to illustrate our distribution of our planetary winds. Right, we assume this is our globe, and let's assume our equator is here at 0 degrees. I'll use the southern hemisphere for the illustration. Then we have the subtropical region, which is at around 30 degrees, and we have the subpolar region at around 60 degrees. Then we have our South Pole at 90 degrees. So the illustration here is such that we have the distribution of pressure belts on a global scale, and our pressure belts are distributed in this way. Over the equatorial region, we have a low pressure region because of intense heating, and around the subpolar, we have a high pressure belt because it's a belt of sinking air. Then around 60 degrees, we have a low pressure, which is the subpolar region. This is caused by mainly the deflective effect caused by Coriolis force. And we have the 90-degree polar region to the south is a high pressure belt. Right. Then because of this distribution of pressure belts, we also tend to have pressure gradient existing between the pressure belts. Right. There's high pressure, there's low pressure, which implies that the winds are supposed to be blown from the high pressure going towards the low pressure. But remember, there is what we call Coriolis effect. the effect of Coriolis, it will cause a deflective effect. It will deflect the winds. So by the assumption of pressure gradient force, we assume that because of pressure gradient, whenever we have a high pressure and a low pressure, the air will blow from high going to low like that. But that is not the reality of the situation on the actual ground, on the actual planetary movement of winds. They tend to be deflected because of Coriolis force. And according to the Ferrell law, our Coriolis effect deflects in the southern hemisphere to the left. And in the northern hemisphere, winds are deflected to the right. That is the Ferrell's law of deflection, which is caused by Coriolis force. So because of that effect, what is going to happen here is from high pressure subtropical region to the equatorial low pressure, the winds are going to slightly turn to the left like this. So which means our winds in this belt, they will be deflected in this direction. That is the deflective direction. And from high pressure to low pressure here, the air is supposed to be blown from high pressure to low pressure, but however, it is also going to be deflected to the left. Again, in this belt, it's going to be to the left. And from high to low, again, our winds are deflected to the left. This is southern hemisphere situation. And this is the distribution of our planetary winds in the southern hemisphere. These winds here, we call them, this is our west and this is our east. These winds here, we call them the tropical easterlies, in the sense that they are occurring in the tropical region and their direction is from the east going to the west. Then these ones here in this belt between 30 and 60, we call them the westerlies, because they are coming from the west going to the east. And these ones originating from the polar region and coming from the eastern direction, they are called the polar easterlies. Right. So we know well that our mid-latitude cyclones, they start around the polar front. The polar front, which is somewhere here. So the mid-latitude cyclone forms as a result of the meeting of the polar easterlies and the westerly winds. But however, they dominate around this area here. The mid-latitude region, we are saying, is around 45 degrees of latitude to the north and to the south. So the dominant planetary winds that we are seeing here are these winds here. These are the winds which are going to influence the direction of movement of the mid-latitude cyclones, because they are occurring in this belt of the planetary winds of westerlies. So the reason as to why, or the reason as to why our mid-latitude cyclones or the cold front is driven from the west going to the east is because they happen to exist under the influence of the westerlies. That takes us to the response for the next question. So they are influenced by the westerlies. Those are the winds responsible for the direction of movement of the cold front or the mid-latitude cyclone as a weather system. Account for the heavy rainfall of 80% at A as the cold front approaches. Why do we experience rainfall there as the cold front is coming and passing? Right, the reason here that we are going to talk about is there's going to be strong upliftment of warm, moist air. Because of the coming of the cold front is going to uplift warm and moist air. And what is going to happen to that moist air? Cumulonimbus clouds are going to form. Because of condensation. We know well that if warm and moist air is uplifted, it will reach a dew point and condensation is going to take place. And in this instance, because of the steep gradient of the cold front, it is going to cause clouds of large vertical extent, which come in the form of cumulonimbus. They are going to form in that area, in the eastern side of our cold front, and hence resulting in heavy rainfall. We know well that cumulonimbus clouds are associated with heavy rainfall. So that is why we account, that is the account for the 80% rainfall at A. Just to the east of the cold front. It's because the advancing cold front here, as it advances towards the east, it is going to cause upliftment of the warm and moist air, and that warm and moist air is going to reach dew point. The moisture will start to condense, forming towering clouds, and those clouds were likely to produce very heavy rainfall. Right, we move on to the next question. In a paragraph of approximately 8 lines, explain how different weather conditions associated with a cold front will have a negative impact on tourists in the Western Cape. We want to look at the implication of the different weather conditions associated with a cold front and their negative impact. Right, what we need to analyze here, we need to look at the different weather conditions first. We need to analyze the different weather conditions which are associated with the coming of the cold front. We know well that if a cold front is coming, it is going to cause excessively cold conditions. Or we talk of very low temperatures. It's one of the weather which is associated with the coming of the cold front. It's going to cause excessively cold conditions. And it's going to cause overcast conditions. There will be full cloud cover. And because of that full cloud cover, it is going to cause heavy rainfall. On top of the heavy rainfall, that rainfall is associated with thunderstorms. And lightning. So, given this situation, we are saying these are some of the conditions associated with the coming of the cold front. And also, we can talk of the cold front bringing in strong winds or the gust winds. So these are the conditions that we can talk about. So we want to analyze how they are going to affect the tourists in the area. So we are talking of excessively cold conditions. These conditions here, they are likely to cause some health complications. If there is excessively cold conditions, the tourists might be affected by some health complications like pneumonia. It's a typical condition which is associated with cold conditions. So the tourists might be affected negatively because of the impact of pneumonia brought by the excessively cold conditions. We're talking of overcast conditions. It's overcast. And that overcast sometimes, it can cause misty conditions. And those misty conditions can cause reduced visibility. And in some instances, if the tourists have gone out, they might result in them getting lost, which is a negative implication. If the tourists are out and we have overcast condition causing misty or foggy conditions in high-lying areas, that is most likely to reduce visibility and the tourists might get lost. Then heavy rainfall, when it's raining heavily, it means the tourists cannot go for activities like hiking. Why can't they go for hiking? The ground will be slippery and there will be dangers of them getting injured if they try to go on hiking when it's raining heavily. The ground will be slippery, that will cause likely injuries on the tourists. Then thunderstorms and lightning. There are high chances of electrocution on the tourists, which is a negative implication. Strong winds, if there are gusty winds, that is also going to affect the tourists. They cannot go for outdoor activities because of the weather. So basically what we need to identify, the weather conditions associated with the cold front. Then we need to look at its implication on tourists. Right, I'll move on to the next question. That brings us to the end of question number 1.3. We move on to question number 1.4. Refer to the satellite image below of a tropical cyclone. Right, this is our satellite image. We are seeing this is the focal point of our satellite image, and this is the surrounding areas of the focal point of the satellite image. And these whitish things, it shows the cloud and the circulation of that cloud. So give one piece of evidence from the satellite image which shows that the tropical cyclone is in the southern hemisphere. The evidence that we have, which suggests us to us that this tropical cyclone is in the southern hemisphere, is because of the circulation. If we check our cloud here, it shows that it's circulating in this direction. So it's because of clockwise circulation. Right, our circulation direction, they differ with hemispheres. Right, if we are to go to the northern hemisphere, we tend to find that in the southern hemisphere, our circulation in a low pressure cell, air circulates in a clockwise direction. Out of a high pressure cell, the air circulates in an anti-clockwise direction. That is in the southern hemisphere. Then in the northern hemisphere is the opposite. When air is feeding into a low pressure, it feeds in an anti-clockwise circulation. Then if air is coming out of a high pressure cell, it circulates in a clockwise direction. That's the difference between northern hemisphere and southern hemisphere in relation to circulation into the low pressure cell and circulation out of the high pressure into the low pressure and out of the high pressure. It's the opposite of each other between the northern hemisphere and the southern. So in this situation, our tropical cyclone is a low pressure cell and the circulation is clockwise in the southern hemisphere. Right. We move on to the next question. Name the area of the cyclone labeled A. Our area A, this is the focal point of our system, which is the eye. That's the eye of our weather system. Right. Why does A subside in area A? Right. I'll try to make an illustration here. We are saying at A, the air subsides, which means there's sinking air. I'll try to make an illustration of a cross-section of the tropical cyclone. Right, on a tropical cyclone, we tend to have the highest towering clouds around this area. Then as we go out of the system, the extent of the clouds will get lower and lower. The same happens on either side of the system, like that. Right, so these are updrafts of air, which is feeding into the system, like this. It's feeding into the system. And what we are seeing here, we are saying the eye of the system is at the center of this whole weather system. And if you check the subsiding air inside here, the center of the system, we tend to find clear conditions existing in the eye of the weather system. We have clouds forming on either sides of the wall, but in the center of the system, there will be clear conditions inside here because they will be subsiding air inside the center of the system. Right, so the question is saying, why does air subside in the eye of the system? What makes the air subside in the center of that system is because there's low pressure at the surface here. We see there's excessively low pressure at the surface. So there's a tendency of drawing air from upper atmosphere to feed into the low pressure here. So because of this low pressure, there's a tendency of air to subside. And what are the conditions in the upper atmosphere? There is high pressure above the eye, above here. So we can see, because there's high pressure and there's low pressure close to the surface here, the tendency is the air has to gradually sink or subside to the eye here. So because there's higher pressure above and there's low pressure close to the surface, the tendency is that the air will feed into the center of the system or the eye of the weather system. Right, moving on to the next question. It's saying, draw the symbol that is used on a synoptic map to represent a tropical cyclone in the southern hemisphere. I'll do the illustration here. Right, what happens here is the symbol that is used in the southern hemisphere. I'll illustrate the two hemispheres. Southern hemisphere, the symbol is like this. This and this. Right. What does the symbol imply? It implies that this is a rotor system or a system that rotates. If this system is rotating, what is the implication? It implies that if air feeds in this direction, the system is going to spin in this direction. And if air feeds here, the system is also going to spin upwards like this. So this will give us clockwise circulation. If air is blowing into this rotor here, it is going to spin in this direction. And if air is also feeding here, it is going to spin in that direction and completely giving us a clockwise circulation like this. Then in the northern hemisphere is the opposite. The weather system is indicated like this and is indicated that way. Also implying that this system is a rotor system which is rotating in this direction. If air is fed there and if air is fed here, this is going to give us an anti-clockwise circulation. So those are the two indications of tropical cyclones on a weather map. In the northern hemisphere, it's like that. In the southern hemisphere, it looks like that. That is how those symbols are portrayed on the synoptic maps. And you tend to find that the focal point here is shaded. In the central part here will be shaded. But what matters most is to know how these rotors are inclined. Right, let's move on to the next question. Explain the formation of high density clouds at B. Right, we go back to our illustration. Our B is here, just outside the eye wall. Our B is here. We are saying there are dense clouds here. Right, why is it that we have dense clouds close to the eye of the weather system? Right, one is because there's strong upliftment. Of warm air close to the eye. If we check, there is very strong winds. The winds are most strong here, and they get weaker as we get out of the system because the winds are circulating just in a clockwise direction around the eye of the weather system. There is strong vertical upliftment here around this area B. And as a result, those vertical updrafts they will lead to high condensation, high levels of condensation. And that will create dense cumulonimbus clouds. That's the situation. Because there's strong vertical upliftment of air, because the air is strongest close to the eye, around the eye wall, the air is strongest. There is vertical updrafts that lead to very high levels of condensation. The air vertically uplifts and reaches condensation level and keeps on going upwards, creating towering clouds. And those clouds will be having high density because of the nature of upliftment and the resultant clouds that form in that particular area. Right, going on to the next question. High density clouds result in torrential rainfall or heavy rainfall. Right, those high density clouds, they result in heavy rainfall. Describe the natural or physical environmental damage associated with torrential rains as it moves over the land. Right, we want to look at the implication on the natural environment. Right. So we are looking at the implication of heavy rainfall on the natural environment. We look at factors like the effect of flooding. The environment can be flooded because of heavy rainfall. It can cause flooding, which will pose negative implications on wildlife and which will also affect the biodiversity of the area. Then we also look at aspects like destruction of natural habitat. The habitat might be destroyed because of excessive heavy rainfall over the land. And also, we can talk of the disruption of the ecosystem. The ecosystem is also affected. The balance of nature is also likely to be affected by the heavy rains over the land. Then also, we can talk of aspects like drowning of wildlife and vegetation. Aspects like soil erosion, it is likely to cause soil erosion that is going to affect the soil on the natural environment. You can talk of aspects like may cause leaching of nutrients, of soil nutrients. So if you check, those are some of the implications that are brought, or we can talk of destruction of soil structure. It can be destroyed or can be negatively impacted because of excessive rainfall. So those are some of the implications that you need to talk about. Remember, our question is specifically on the natural environment. So we are looking at nature. How is nature affected by heavy rains? Right, we move on to the next question. It talks about the Berg winds. Right, we don't need to read through the extract. We need to go to the question straight. What are Berg winds? Right, when you are describing the Berg winds here, or when you are ultimately giving a description, we need to address the basics of the idea of Berg winds. Right, when you talk of Berg winds, we are saying, what is the nature of the winds? In terms of nature, we are saying these are hot, dry, gusty winds. They are hot and they are dry, meaning to say they don't have moisture, and they are gust winds, meaning to say they will be strong winds. Right, that's their nature. And we also need to analyze how they come to exist. How do they form? Right, Berg winds, they do form because of adiabatic heating of air descending from the plateau. And this air is driven by the Kalahari high pressure. Air coming from the Kalahari high pressure over the plateau is descending the escarpment and is attracted to the coastal areas. What drives the air is because of the presence of the coastal low. And also what we need to analyze here is where are they experienced. This is a regional wind. It's a specific wind which affects a specific region. So they affect coastal places of South Africa. Because it's not a planetary wind which is common across the globe. It's a regional wind, just the same as the Fohn winds or the Chinook or the monsoon winds over India. So the Berg winds are typically winds for South African coastal areas. So that is basically what we must address for you to give a composite definition of the Berg winds. Right, I will move on to the next question. State two factors evident on the map that promotes backwind conditions. I think from what we have explained, now you can see the factors which promote the formation of the backwinds. We have a high pressure over the interior, which we said is the Kalahari high pressure. Then we have the coastal low over Durban here. It facilitates pressure gradient. There is high pressure over the interior and there's low pressure, which implies that the air has to come from the high pressure interior and go to the low pressure coastal. And also we have the escarpment here. As the air descends, it has to heat up adiabatically. So these three, number one, the high pressure over the interior, number two, the low pressure over the coastal area, and number three, the presence of the escarpment. Right, we move on to the next question. According to the extract, why does the temperature of the air increase as it blows from Johannesburg? We go to the extract. The extract says, where it undergoes heating caused by adiabatic process. That is how the air heats. It heats up because of the adiabatic process. So that's the response. Determine the expected air temperature at Durban due to the associated backwind conditions. Let's go to our extract and check the expected. The air parcel is at 20 degrees Celsius. Descending from Johannesburg to Durban, that would heat up by 15 degrees Celsius. Because we are expecting a decrease in altitude by 1,500 meters. So because of the rate of adiabatic heating, which is plus or minus 1 degree Celsius for every 100-meter descent, we tend to find that it will heat up by 15 degrees Celsius as it descends over an altitude of 1,500 meters. So addressing our question in this instance, we are saying the expected air temperature is going to be the initial temperature, 20 degrees Celsius over the plateau, plus, because of adiabatic heating, it is going to gain 15 degrees Celsius as it descends, which is going to give us a total of 35 degrees Celsius. That is going to be the expected temperature as it reaches Durban. Why is the threat of wildfires greater during the day when backwinds occur? Right. Why do backwinds most likely to cause fire conditions over the coastal areas during the day? Right. We can justify that by looking at the frictional effect. During the day, we understand daytime conditions. During the day, we expect that there's insolation and ground is warm. So because the ground is going to be warm, because of insolation, the friction between the warm ground surface and the backwind will spark fires. It is most likely to spark fires during the day. The ground is warm, and also the hot and dry air is ultimately going over the hot ground surface. That is most likely to spark wildfires. And also, we note that during the day, there will be a situation of dry vegetation. Dry vegetation during the day. Vegetation will be dry, and that is likely to facilitate the spread of fire. Because the vegetation is dry during the day, there's no accumulating moisture over the vegetation. It has evaporated during the day because of insolation. Then it will imply that fires can easily spread over a dry matter because the vegetation does not have any moisture. There is high levels of evaporation during the day. So that is going to facilitate the spreading of the wildfires. Right. Explain why backwinds are associated with lower agricultural productivity. Why do they impact negatively on agriculture? That is number 5.6. This is 155. Then going to 156. What are we saying here? we are saying, why are they going to likely cause low agricultural productivity on the farms? Right. We look at the implication. They are going to cause increased evapotranspiration. There's going to be increased moisture loss from the crops and also from the soil. And that will lead to water stress on the plants. The plants won't have sufficient moisture because they are losing a lot of moisture through transpiration, and also the ground is losing moisture through evaporation by the increased heat conditions caused by the back winds. And also because you said there are gust winds, the back winds, they cause damage to crops. Damage to crops due to strong winds. The strong gust winds are going to cause damage, physical damage to crops, resulting in low yields. And also, hot and dry conditions, how do they affect hot dry conditions? How do they affect crops? They reduce crop growth, and yields. Crops are exposed to excessively high hot and dry conditions. That is going to affect the growth rate of the crops, and apparently that is also going to impact on the quality and quantity of the yields, resulting in the negative implication on the outcome of agricultural activities in the coastal areas. Right, that brings us to the end of our climate and weather question. We're moving on to question number 2, which is a question on geomorphology. Right, this question is based on drainage patterns. We have pattern PQRSTU. Right, I'll just try to summarize the drainage patterns before we move on to the questions. Right, this pattern, as you are seeing it, it resembles a tree and its branches. This is called dendritic. This one that we see here, Q, we are seeing that the streams are radiating from a focal point, which is likely to be a high-lying area, for example, a volcanic dome. And they will be radiating outwards from that high-lying area, which is a focal point where their sources are. It implies that this is what we call radial pattern. And this one here, we are seeing that there's a lake at the center, and the streams are starting from high-lying areas feeding into a low-lying area. This is what we call centripetal. Right, we move on to the next one. S. S, we are seeing that the streams are meandering or bending at right angles, and they're also joining the major stream at right angles. This is what we call rectangular pattern. Right, and T, we are seeing that the main stream is longer, but the tributaries are shorter, and they join the major stream at right angles. This is what we call trellis. And lastly, we are seeing that these streams are running parallel to each other. This is what we call parallel pattern. Right. So, what is the likely underlying rock structure of the areas over which these different patterns develop? We tend to find that the dendritic pattern develops over rocks of uniform resistance. This one forms over rocks with uniform resistance, and radial forms in dome areas where there is a dome feature like a volcanic dome. And also these ones, they form in areas where we have low-lying areas like the swamps, the swampy areas, or where we have, for example, a lake which is surrounded by, or in situations of the castor basins, in basin areas. That is where they form. Right, then rectangular, it forms where we have fractured or cracked hardened resistant rocks, mainly igneous rocks. Then trellis, this one, you can see, it implies that there is a valley and some high-lying area surrounding a valley. It forms in areas which are either folded or areas of major faults. Then this one, it forms also in areas which have got parallel folds. Right, or parallel folds. Right. That is basically the idea behind the drainage pattern. So we want to use that knowledge to try and apply it and answer the questions that are following to that. Drainage pattern P is known as dash pattern. We have answered that. Drainage pattern P is dendritic, which is A. In sketch dash, rivers flow towards a low-lying central point. Low-lying central point like a basin or a swamp area, that is R. Our correct response is C. Drainage pattern Q is known as dash pattern. Q, we are here. We say that is a radial. Right, moving on to the next question. Drainage pattern S is associated with, where is S? Our S is here. We said it's fractured or cracked igneous rocks. So what is the correct response? Jointed igneous rocks. Right. Then 215, it says tributaries in sketch dash join the main stream at acute angles and resembles the branches of a tree. Automatically, this is this one here, dendritic, which is pattern P. So our dendritic is on pattern P, which is item A. 216 in sketch dash, these streams flow alongside each other in areas of steep folded bedrock. Steep folded bedrock areas flowing alongside. This is parallel, which is U. So our response here is D. The underlying rock structure of drainage pattern T is, what is drainage pattern T? We check with drainage pattern T, right? This area, this we said is an area of major faults or folded areas. So it's major faults. Right, in drainage pattern Q, the stream order at X is, right, with when we talk of stream ordering, I will try to illustrate here how we calculate stream ordering. And could dash increase or decrease with heavy rainfall? Right, what happens with stream ordering? When we're talking of stream ordering, we are talking of the arrangement of streams in a drainage basin or the ranking of streams in the drainage basin. We have stream number 1. What we call stream number 1 in drainage basin is an independent stream. A stream that is not fed by any other tributary. It's a stream without tributaries. That is stream rank number 1 or first order streams. So if we have a stream without tributaries meeting another independent streams without tributary, that gives us stream number 1 plus number 1. The order becomes number 2 at the confluence of those two streams, which implies that the stream which develops after the confluence is ranked number 2 in that drainage basin because it is comprised of 2 independent streams. Right. Then if we have we have stream number 2 combining with stream number 1, it remains stream number 2. Then if we have stream number 2 combining with stream number 2, the order goes to third level. Then if we have 3 plus 1, it maintains 3. If we have 3 plus 2, it maintains 3. If we have 3 plus 3, it goes to the next order 4. And the ranking goes like that. That is how we do stream ordering. So what I'm saying here is, if we have like this, independent stream, this is stream number 1, this is number 1. When they join from here, this is now number 2. If number 2 is joined by an independent stream, it does not change. It remains as number 2. But if number 2 is joined by another number 2, how do we get number 2? It's because there's number 1 and number 1 giving us number 2. Now here at this confluence is now number 2 plus number 2. The stream which develops here is now stream number 3. That is how we are doing our ordering in the drainage basin. And if you want to analyze the order of the stream after heavy rainfall is going to cause an increase in the number of streams in the drainage basin. So apparently, the more the number of streams, the higher the order a stream is going to attain. Like, if we look at stream number 1, it's number 1 because there is no stream feeding into it. But if there is a stream feeding here, because of heavy rainfall, another stream develops while this one is going here, it's no longer number 1 here. Number 1 is now there and there. This now goes to number 2. And again, if this happens on this side, this is now number 1. There are new streams developing. This becomes number 2, which means it's no longer number 2 here because there's number 2 and number 2. This is now order number 3. which means with the increase in rainfall, it also implies that the order is going higher and higher with the number of streams developing. The increase in the number of streams developing in the drainage basin is also likely to cause a change in the order of the streams in the same drainage basin. So our correct response here, let's go to the illustration and check. Right, in the illustration, we are seeing that our X point is indicated at that particular point. So let's try to identify the order of the streams upstream of the point X. This is stream number 1, and this is number 1. They are giving us number 2 here. This is number 1, and this is number 1, and they'll give us number 2 here. So after this confluence, we are saying it's now stream number 2 plus stream number 3 as 2 plus 2, which means we are now having 3 here. So the order then is a third order stream and could increase if there is increased rainfall like what we have illustrated here. So item 2 and item 3. Item 2 and item 3, they are on C. That is the correct response. That takes us to the end of question number 2.1. We need to move on to question 2.2. Right, going to 2.2, the sketch that depicts turbulent flow. Turbulent, we are saying the river bed is uneven, resulting in an undulating flow in the river, or the discharge is unstable. This is typically of turbulent flow. The fluvial process associated with turbulent flow is erosion. When there is erosion, the river bed becomes uneven, such that the flow of the water is also uneven and is turbulent. Right, the fluvial feature associated with turbulent flow is a rapid. We know that rapids are a short version of a waterfall, and they are likely to cause the flow to be unstable. The sketch that depicts a cross profile. Cross profile is a view of the river from one bank to another. So this one here is from the source to the mouth. This is the longitudinal profile. So the cross is Z. It's showing from one bank to the other bank of the river. An example of an ungraded river profile: when a river is graded, it has a smooth concave shape, like from the source to the mouth here, like what you are seeing on Y. It's a smooth concave shape. This is a graded profile. But when a river is having some temperate base levels along its longitudinal profile, that gives us an ungraded river. Like, for example, if there's rejuvenation taking place in a graded river, it goes back to becoming ungraded, and that is going to be the longitudinal profile status of that particular river. Right, number 2.26, dash of rivers can change the grade of a river from graded to ungraded. That is rejuvenation. I think I've talked about that. Right, a waterfall is an example of dash base level. It's a temporary base level. Waterfalls exist along the river channel when they have not attained a grade. When the waterfalls are ultimately eroded, the river attains a smooth concave shape without waterfalls, without rapids along the channel, or without lakes in the channel, because those are temporary base levels of erosion. Refer to the sketches below of a braided stream and a delta. Right, that is a braided stream, we can see there, and that is a delta. Right, these are both features that are found in the lower course of the river. Braided streams and deltas form when the dominant fluvial process is deposition. Deposition causes the development of braided streams and the deltas, because the rivers will be depositing loads in the river channel, resulting in distributaries or in a network of channels within the same channel. Right, one physical similarity. How are they similar, those two? What are the physical similarities between deltas and the braided streams? Right, if we check there, we can see, let's look at the diagram. Right, this is a delta. We are seeing this area here and this area here. What are the similarities? We can note that here, the similarities that we tend to find, we have multiple channels. The channels will be multiple. Like here, you see another channel goes there, another channel goes there, another channel goes this side. And also here, this is one channel, another channel will go there. They are a number of channels. So we have multiple channels. And also the other feature, we have segments. deposition, those the islands, the sediment islands. These ones here in black, these are our islands, and the same feature of deposition are these ones on the delta, these sediment deposits. And also the other similarity is that of a network of distributaries. We have distributaries forming. The stream is branching into smaller streams. The main stream is branching into smaller streams, what we call the distributaries. The distributary is the opposite of a tributary. Remember, a tributary feeds into the main river, but when a main river is splitting into smaller streams, that becomes a distributary. So both the deltas and the braided stream, they have a network of these tributaries, right? Those are the physical similarities, right? Give two reasons why braided streams are common in the lower course of the river, right? The justification why we have the braided streams in the lower course of the river is there is reduced gradient. Which leads to reduced velocity. When the river ultimately is flowing over a flat-lying area, it means the gradient is reduced and apparently the velocity of the river is also reduced. And for that reason, we have high sediment deposition. Deposition happens whenever the river's energy to transport load falls below the minimum required. The river becomes overwhelmed in transporting the load. What makes the river effectively carry the load is because it will be having high velocity. If it's flowing over a steep gradient, it means it has more energy. It has more energy to transport because of high velocity of the flow of the discharge. But if it gets to low-lying areas, if it gets to flat areas, it means the river velocity gradually weakens. And that is also going to weaken the transportational capacity of the river. And as a result, the river is going to start to deposit load along the channel. So that is the situation of the causes of the braids in the lower course of the river. Right. We move on to the next question. The next question is saying, why do deltas not form in all rivers? It's not all rivers that do have deltas as they approach their mouth. Some rivers don't have. They just feed directly into their mouth without creating those multiple distributaries. What might be the geographical cause why some rivers do not have some deltas? Why do deltas not form in all rivers? Right. I'll give the reasons and just try to explain. Right. One reason is strong offshore currents. Right. If a river is exposed to strong offshore currents where it reaches its mouth, automatically it means the deposited material is going to be transported into the mouth and not accumulate before at the mouth because of the strong offshore currents. They prevent the formation or they prevent the accumulation of deposits. Right, that is reason number one. And also the other reason is river flowing into deep water. For a delta to form, the river must be flowing into a mouth which is at almost the same altitude as the river that is feeding into. such that there is effective deposition taking place. But if a river is flowing deeper into its mouth, then there's automatically no chance of formation of a delta, because there will be energy there for the river to discharge its load into the mouth without accumulating deposits before the mouth. So river flowing into deep water, like for example, when there is a fall in sea level, when the sea level falls, automatically deltas cannot form, because the river will be plunging into a deeper, will be flowing into a deeper source, into a deeper mouth. Right. Then we also have a situation of low sediment load. There are some rivers that have got very low sediment load, like rivers flowing over areas with hard and resistant rocks. In most instances, if the course of the river is predominantly over hard and resistant rocks, those rivers cannot effectively erode, and they do not have much load with them. So for deltas to form, it means they must be having sufficient load to deposit such that they form the delta. But if it has less load, it means the deltas are less likely to form in those rivers. Then you can also talk of tectonic upliftment. Because of tectonic upliftment, if there is tectonic upliftment, it means the gradient is going to be steeper towards the mouth of the river, and hence there is no effective formation of deltas. If a landform is uplifted, then automatically it means we will have a steeper gradient as we are going towards the mouth of the river, and then because of the steeper gradient, the river cannot effectively deposit material, forming the deltas. Right, then we got the last question. Explain why deltas are suitable for agriculture. Why are the deltas suitable for agriculture? What's the rationale for deltas being suitable for agriculture? That is number 235. Right. When you look at deltas, they have fertile soil. Where does the fertile soil come from? It's because of sediment deposits. Alluvium that is deposited in the deltas bring with it some fertile soil and fertile matter that is going to decay and contribute towards the fertility of the soil. So for that reason, the soils will be fertile because of the deposits. So it's ideal for farming. And then the other reason is water availability. Water is readily available. If you check on the delta, we have quite a number of distributaries where you can easily access water. So for that reason, we can effectively farm in the delta area because its availability of water. And also we can look at the terrain. It's a flat terrain on a delta, which can also allow easy farming and use of machinery. So for those reasons, you can safely say a delta is an ideal place for farming. Right, going on to the next question. This is a question on river capture. Right, these are the two situations where one river is advancing towards the other. A river in a low-lying area is more energetic, river A, and it advances through the watershed and manages to intercept the waters of B. Right, we are going to ask to the questions. What is headward erosion? Right, I will try to explain on headward erosion. That's number 2.4.1. When we talk of headward, it's a type of erosion which is responsible for lengthening a river channel. How does it operate? Headward erosion operates in the sense that the source of the river migrates upwards. So we are saying if a stream is like this, the source is here. If it's migrating upwards, it means maybe the next season, the source is now here. Maybe the next season, the source is there. Next season, the source is there. So we are seeing that the total length of the river is accumulating. This is headward erosion. We have other types of erosion. besides headward, just for clarity purposes, we have what you call lateral erosion. Lateral erosion is sideways. Is responsible for widening the river channel. When a river channel becomes wider and wider, it means the erosional processes are happening sideways. Like let's say this is the initial channel and there is erosion happening on either side. We tend to find that maybe next season, the river is now here, it's now wider. And with increased erosion on the sides of the river, maybe the river channel will end up like this. It's getting wider and wider. That is lateral erosion. Then we have what we call vertical erosion as another type of erosion. Vertical erosion is responsible for deepening the river channel. What happens is if the river channel is like this and there's headward erosion, headward open happens, a vertical happens vertically like this. Maybe the next season, the river is now there. Next season, the river is there. Next season, the river is there. You see, it was here at A, it went to B, it's now at C, now it's at D. The river is becoming increasingly deeper and deeper. That is vertical erosion. Right, that besides the point, that was just an explanation to the other types of erosion. Right, moving on to the next question. State one factor evident in the sketch that would promote headward erosion in stream A. What promotes headward erosion in stream A? A factor which is evident. Right. This stream, if you check, which promotes headward erosion, this stream A, is flowing over a low-lying area. And automatically, if a stream is flowing over a low-lying area, and there's steep gradient here, these two features, this river is flowing in a low-lying area, and there's steep gradient towards the watershed. It implies that a stream which develops towards the watershed here will have more energy, will be energetic, such that it keeps on advancing headwardly until it reaches that bylying area. So because of the river flowing in a low-lying area here, and because of the steep gradient on this side, those are the factors which promote headward erosion. Why is stream A referred to as the captor after river capture? Stream A here is regarded as the captor. It captures the water of B. Right, why is it a captor? Is because it intercepts or it robs the waters of stream B. That is why it's a captor in the sense that is capturing. Why is gravel found at the wind gap after the river capture? Right, we find gravel in the wind gap after stream piracy has taken place. Right, the gravel is evident of the remnant of former river activity. It shows that there was an active river there which was flowing, which was depositing its material along its channel. That is the evidence that we find. It's evident of the previous river. And also it's deposited sediment. The gravel is the deposited sediment of the stream before capture. It shows that it's a material that was being deposited by the river before stream piracy took place. And also it shows that it's evidence of the presence of a former river in that area. And also it's an indication of stream piracy in simple terms. It indicates that there's stream piracy which has taken place in that area. because this a remnant of the activity of the river, and also it shows that it's deposited material which was once deposited when there was still an active river before the stream pirates took place. Right. The next question is saying, explain how the fluvial processes would change in stream A after river capture. Right. In stream A, this is the capture stream. How are the fluvial processes going to change? Right. We want to analyze the fluvial processes that are going to change there on the capture stream. In the capture, the fluvial process that we're going to look at, we want to look at discharge, or the volume of water in the river. We also want to look at analyze the velocity of the river. We might also need to analyze erosive power or erosion. And we might also need to analyze deposition. Right, when the river has captured headwaters of another stream, automatically it means the volume is going to increase because it now has extra supply of water from the captured stream. The velocity is going to increase because it now has extra water which has been captured from another stream, and apparently that is going to cause an increase in the velocity of the river. Right. In terms of erosive power, the erosion is going also to increase because now the river has high velocity. It means it has more energy and likely to cause more erosion happening. And lastly, on deposition is going to decrease because now there is high energy. It means the river now has capacity to transport its load. So there is less deposition that is going to happen in that particular river. So those are the fluvial process changes that are going to be realized because of the effect of stream piracy on the capture stream. We move on to our last part. Is talking about Northwest communities near mines concerned about water pollution. Right. According to the extract, state two ways in which mines pollute rivers. We just need to go to the extract and check ways through which mines pollute rivers. Right. He's talking about mine chemicals are a great threat to the quality of ground water and water that runs off the surface into rivers. So mine chemicals is number one. Then mining waste can pollute water through surface runoff and seepage into mine dumps. Right. So we are seeing that mining waste and mine chemicals, those are the two ways in which the mining activities, they do pollute rivers. Quote from the extract, one health risk that mining poses for humans. It says here, exposure to metals can lead to numerous health issues, including stomach illnesses and an increased cancer risk. So that is how health risk, how mining causes or poses health risks. It exposure to the metals automatically from polluted water can lead to numerous health issues, and those health issues include stomach illnesses and an increased cancer risk. Explain the negative impacts of mining on the river system. Right. When I'm explaining the negative impacts of mining here, we need to analyze how the mining activities can impact on the natural operation of the river system. We talk of chemicals. If there are chemicals added to the river because of mining activity, how are they going to affect? They affect water quality. The quality of water is negatively impacted by chemicals in the river. Or we can also talk of the effect of the chemicals on aquatic life is also going to be disturbed. Aquatic life, it's a negative impact. Then we can also look at sedimentation of rivers because of deposit of sediments of mine dumping. into the rivers. It causes sedimentation. It can cause increased sediment load. And that is going to change river morphology. We'll end up having some features, some fluvial features, which are not likely to be in the river at a certain stage. Like, for example, we find that we now have braids in the middle course. That is because of maybe waste which is being dumped into the river. And because of increased sediment, the river cannot effectively transport that load. And that load accumulates within the river channel, creating a network of distributaries or a network of channels that will change the river morphology. The morphology of the river will now be changed. We now are now finding landforms, fluvial landforms of the lower course in the middle course because of the excessive sediments that has been deposited into the river through mining activities. Then we can also talk of habitat destruction. For example, destruction in the river banks or around the wetlands. And also the aquatic ecosystem is negatively impacted. So those are some of the effects that mining activities can pose on the river system. It can also destroy habitat around the river systems, like in the river banks or in the wetlands, or it also disturbs the aquatic ecosystem. Right, we are moving to our last question. In a paragraph of approximately 8 lines, suggest measures that mining companies can implement to manage the impact of water pollution on rivers and humans. That is number 2.5.4. Right, 2.5.4. Right, what can the companies do to reduce the impact of river pollution? Right, they can implement effective water management system, implement effective water management systems. For example, we can talk of treatment of water or recycling. Recycling of wastewater. Those are effective management of strategies of managing water. They can try to treat water. In case of water pollution, then there must be ways of how to treat water to make it reusable and conducive for human consumption. And also recycling wastewater, that can be a strategy that the companies can implement to lessen the burden on the people. And we can also look at monitoring. They can monitor water quality regularly and take corrective measures. They must always make sure that they are checking on the quality of water to check if there are any pollutants from their activities which are leaking into the water, so that if there is any evidence of pollutants leaking into the rivers, then they must take corrective action in their operations to ensure that there is no leakage from their mining activities, which happens and which tends to pollute the rivers. Right. Then we can also look at usage of best available technologies. Usage of technology and practices to minimize water pollution. The companies must research into methods of preventing pollution into the rivers. They should find sustainable measures of mining which do not harm and pollute the water sources or the water bodies. So they must practice ways of sustainable river management, and also they must research into new technologies to find ways of sustaining the rivers and not causing harm to the water sources, and also engaging with community. They must engage local communities and provide information on water management practices. That is the other way that the companies can engage. They can engage local communities. They deal with the local community to find measures of how they can manage the water resources available and how they can sustain the available water resources. Then lastly, we can talk of rehabilitation. Rehabilitate mined areas to minimize the risk of water pollution. Right, for that reason, rehabilitating mined areas, there are some areas that would have been formerly mined that are now disused, and because of the chemicals that were used in those areas and on those mine dumps, we tend to find that they continuously cause harm to the environment because of acid mine drainage. So as a result, those companies must rehabilitate those areas. They must try to find ways of rehabilitating those areas and make them environmentally friendly in a way that they do not continue causing harm to the water bodies. Right, that takes us to the end of our section A on geomorphology. Right, we move on to section B on geographical skills and techniques. But unfortunately for this discussion, we do not have the map for this paper. So what I'm going to do with this discussion, I'll just try to explain how we get through some of the questions and also try to illustrate where it can be illustratable, where it is possible without the map. Right, that is the general information on Estcourt, which is a town in KwaZulu-Natal with those coordinates 2900 south and 2949 to the east. Right, that is longitude. The first question is saying, what is the distance by railway to Frere from the boundary of the mapped area? What you just do there is the map distance in centimeters. You measure the distance. Measure your distance in centimeters, the map distance. You want to convert this. If you are using a topographic map, to convert directly from the map distance to the distance in kilometers, you multiply by 0.5 kilometers. That's the scale of the topographic map in kilometers. If it's an orthophoto map, you multiply the map distance in centimeters, you multiply it by 0.1 kilometers. You get your answer directly in kilometers. Or you can also use the line scale of the map. Like for example, you don't have a ruler, you can use a straight-edged paper. You check the distance from the map and then you transpose it to the line scale to check the distance on the actual ground. Right, the next question is saying, which illustration below represents the map index for topographical map of Estcourt? Right, let's say for example, the map is 29 B. What does that mean? It means this is latitude value in degrees. So which means it falls on the 29 degrees south latitude. Then this, it means the 29 for degrees longitude is 29 degrees to the east. Then this first B, it means is a big block subdivision. Then the last letter, it means it's a smaller block subdivision. So since our maps have got the same indications of our latitude and longitude, responses are all correct. So 29, 29, all of them are correct. Then what we need to check is the bigger block B and the smaller block B. Bigger block B is here, and the shaded area has got D. This is BD, 29, 29, BD. This one is 29, 29, bigger block B, smaller block B. If this is our map reference, it means this is going to be the correct response in that instance. Using it as an example, this is 2929A, bigger block A and smaller block A. This is 2929, bigger block C and smaller block B. So these are the references of these four given block references. Moving on to the next question, says calculate the length of the Wagon Rift Dam at F. You do the same, you measure the distance, and you multiply. If you want the map in distance, in meters on a topographical map, you multiply by your map distance, you multiply it by 500 meters. Measure your map distance in centimeters and multiply it by 500 meters for a topographical map. If you are using an orthophoto, if you want your distance in meters, you measure the distance, you multiply by 100 meters. You get your answer directly in meters. Right, then the next question is saying calculate the magnetic declination for 2025 using the information, the following information. Difference in years, if you check on the map information, that map is 24, was produced 24 years ago, and the information there is for the last 24 years. So it means difference in years will be 24 years from that current year on the map to 2025. Then the mean annual change, you also check there. So what you need to do for you to get the total change, you need to get total change. Total change, you get it by multiplying the difference in years by the mean annual change. So in this instance, our mean annual change is 9 minutes to the west, and our total change is 24. So for us to get the total change, it means we are saying 24 times 9 minutes to the west. And that is going to give us a total of 216 minutes to the west. Converting this to degrees and minutes, we divide this by 60. If we divide this by 60, we get 60 goes there 3 times to give us 180. So which is 3 degrees, and the remainder is going to be 36 minutes. So this is our total change. So you check on the angle of declination in the year, on the map. At the bottom of the map, you check the year, the declination angle. So you are now saying for you to find the magnetic declination for 2025, you say the angle on the map, the angle indicated on the map, plus the total change, which is 3 degrees 36 minutes. You get your magnetic declination for 2025. Right, refer to the orthophoto map. Draw a rough cross-section from 6 in block A4 to 7. When you're drawing a rough cross-section, just be mindful of the heights. You just check the general heights. How are they inclined towards each other? Where you see your contour lines are closer to each other, it means that is a steep sloping area. Where you see your contour lines being general, being further apart, that implies that it's a gently sloping area. That is how you can draw a rough cross-section. Then, is there intervisibility? When you're talking of intervisibility, you are saying, can you see 0.7 from 0.6? So you check the nature of your cross-section. Let's say, for example, your 0.6 is here and your 0.7 is here. And your cross-section is giving something like this. It implies that it's a flat-lying area. It means in this area, there is intervisibility. You are able to see 7 from 6. But let's say, for example, again, your cross-section is giving you 6 here and 7 is here, and your landscape is looking like this. automatically there's no intervisibility because this one is an obstruction. This area is high-lying when comparing 6 to 7, such that you cannot see 7 from 6. There's no intervisibility in this instance. So you just have to check the nature of your cross-section and see if you are able to see one point from another by comparing heights between the two features. You can also determine intervisibility even without drawing a cross-section. You just check the heights. You draw a straight line linking the 2 points and check the heights between the two. If there's a higher height between the 2 points compared to the points that you want to see, then automatically there's no intervisibility. Name the wind that is likely to blow at night between G and H. Automatically, our two kinds of winds, if it's a valley situation, we are saying in a valley, during the night, we have a katabatic. And during the day, we have anabatic. That is a valley situation. Give one reason why this wind will develop in this area. Since we don't have the map, we don't have justification. But the justification is in a valley condition, at night, the valley sides, they cool because of long wave radiation, they lose heat. And as a result, in a valley situation, they will now be having a situation of a high pressure on the valley sides and a low pressure in the valley floor, such that because of pressure gradient, the air blows from the valley side going into the valley floor. Right, we are just generalizing since we don't have the map to give a proper explanation to the situation. Right, the rate of evaporation will be less in area 8 or 9. With that, we refer to slope aspect. You need to check on slope aspect on the map. Check, when you're talking of slope aspect, you are looking at the inclination of slopes. Which side is faced by the slope? In the southern hemisphere, we know well that north-facing slopes are warmer, and that is where we're likely to have high evaporation. If it's a south-facing slope, it means they are cooler, and then there will be less evaporation. That is the justification to that question. Give evidence from the orthophoto map for the low rate of evaporation in this area. The justification there you find on the map information provided, and you relate it to slope aspect. Right. Refer to Wagon Drift Dam on the topographic map. Identify one strategy that was put in place to limit the negative human impact. Unfortunately, we cannot answer that without the map. Refer the topographic map. Identify fluvial feature 10. Then fluvial feature 11 is known as the outer bank or inner bank. Unfortunately, number A, we cannot answer it. But with this one of the outer bank and the inner bank, I will make an illustration and explain. If it's a river channel, and you are seeing there's a meander, let's say the river is going like this, and there's a meander here, like this, and then there's a meander, like this. And maybe feature 11 is on either side. Let's start with this side here. Let's say this is Y, and this is X. If the river is bending like this is what we call the outer bank. If a meander is like this, the part which is on the outer part is the outer bank, and this one is the inner bank. So, based on the map information, you can find out on the meander which one is the outer or which one is the inner. Why will this bank be associated with fertile soil? Automatically, the bank with fertile soil is the inner bank here, this one. Why will it have fertile soil? Is because there's deposition taking place. The alluvium which is deposited will be having nutrients, and apparently it's going to lead to fertility of this. On this side, on the outer bank, there's erosion taking place, and here on the inner bank, deposition takes place. So because of deposition, automatically it means it is going to create fertile soils. Right, then we go to GIS question. Our first question is saying, what is data layering? When we're talking of data layering in terms of GIS, we are saying it's projecting different data sets on top of one on top of another. When we're talking of layering, we are projecting different data sets on top of each other to see their relationship. We can compare different data sets, maps of different data sets by projecting them one on top of another to show how they relate to each other. That is data layering. Then identify two infrastructural layers in block B1 that would promote farming. Right, unfortunately, we don't have the map, but automatically we need to check on infrastructure layers that are in that block. Like you can check on infrastructure layers like, are there layers on roads? Are there roads or are there transport network? It can affect farming. Roads are needed for transportation of the final product of raw materials or workers to the workplace. Or you can check also if there's irrigation infrastructure, like if there are furrows, if there are reservoirs, if there are any other source like dams for irrigation. Irrigation infrastructure is another data layer which supports agriculture. And also you can check if there is any storage facilities like the silos. They also infrastructure supporting farming. So you can check if there are storage facilities like the silos. You can check if there are road networks or transport networks, and also if there's support of irrigation infrastructure in the area. Just as suggestions, since we don't have the map. Right, we move on to the next question. Define the concept remote sensing. When you're looking at remote sensing, this is a geographical concept, a GIS concept, which relates to when you're talking of the remote sensing. We are looking at a situation whereby we gather geographical data from a distance or without contact with the geographical space. We want to find information about a different geographical space, but we are not there physically. We can get that information from a distance through remote sensing means. For example, remote sensing can be done through satellite images, satellite imagery, satellite imagery. Or we can do remote sensing through the usage of drones. We can get information from a distance. We can fly a drone, it can capture images that can give us geographical information, or we can get geographical data through using a drone. Or from satellite images, we can find out information about different geographical spaces without us getting there physically. That is remote sensing. Right, moving on to the next question. Refer to block C1, C2, D1, D2. How would remote sensing assist the town's emergency personnel in the event of flooding of the Bushman's River? Right, we are just generalizing since we don't have the map. How can they use remote sensing in that particular area when there's a flood? Why we need remote sensing during flooding? What can we use remote sensing for during the flooding session? Like, we can use remote sensing to identify areas of need. As an emergency service of a town, we need to find areas which are at dire need, which need to be rescued, or areas which need to be given assistance. So we can actually see those areas through remote sensing. And also, we can plan evacuation routes. We can analyze which route is more is accessible, and then we can use those routes to evacuate the people from the area. And also we can use remote sensing to monitor flood levels. We can use remote sensing to monitor the flood water, like monitoring the levels of the flood waters without getting into contact with the actual ground. So basically, those are some of the basic needs of using remote sensing in a flood situation. Right, that takes us to the end of our discussion. I hope the discussion is going to be helpful for you as you prepare for your examinations for paper 1, be it prelim examinations, be it June examinations, be it the final examinations. That will still be the same ideas or the same concepts being examined. I hope this is going to assist you in your